1 second. No, didn't get it in. There we go. Is it working?
No, it's not.
Oh, this is.
Yes. Oh, yes, sir.
It's rubbing against my neck. Very comfortable. Okay. Hi, everyone. I'll start thanking the organizers for this really nice workshop. It's really a pleasure to close it. And, well, I hope at this point you're already more familiar with what we do in Nottingham in terms of experiments, not only in theory, right? I'll walk you through this new method that we're developing, and I'll try to place it under the umbrella of experiments and also theoretical work that's going around, starting really with why would I need this new method called multiplexed digital holography that was in the title, right? So we heard extensively of the use, the importance, and how good analog gravity can be to raise questions about fundamental physics. Silke brought that up, and several other talks approached that from a theoretical point of view, I would say. But also Leonardo and Pietro showed some very nice experimental results showing this new direction that Nottingham is taking, right? But then it's quite clear for us that, or I hope at least it's quite clear, that to really study this analog simulators in classical or quantum fluids, we have to very well reconstruct these effective field theories, right, that we talk so much about. In our case, this effective field theory resides on the interface of the fluid, so what's important for us is to reconstruct that interface, right? So I put here some of the methods we already use in the lab. So one is the N-shape, which is patent pending that Silke developed several years ago, where you have to put a fluorescent dye in the fluid, so contaminate the sample, and then you can reconstruct waves here in the order of millimeters or centimeters, down to a resolution about of 1 millimeter. But you also have Fourier transform demodulation that Leonardo introduced, where you put a pattern behind your sample. This is the case of the two-fluid sample that Sean and Sylvia discussed earlier today, where you can get the resolution of the interface. They also use this in the helium experiment. In this case, you can measure waves around 1 millimeter to 1 micron. So you have quite a large range, about 3 orders of magnitude. But then the question remains, as brought by Pietro, what happens when we make things smaller, right? Or we want to probe even further these effective field theories. So, for example, study these ripples or surface waves in thin films of helium, or even just in the large sample of helium we already have. Maybe we want to understand better what's the initial state of that effective field theory. So we need to learn about the noise on that interface before doing the experiment. Or in our case, it was really a choice of downsizing the experimental setup. We can't keep building bathtubs of 3 by 1.5, right? So it made sense to now develop new setups that are more current to our purposes. And in particular, the helium was a great example of it. Now, of course, from the methods I presented, there are some practical limitations. So you have sample contamination, which I would say should be avoided if you can. Our resolution so far is in the order of microns, as Pietro and Leonardo presented, but also Sylvia and Sean. You might need multiple separate components. What I mean by that, you need a pattern under the sample, you need appropriate lighting, you need a good resolution camera. So there's a lot to consider to then use the current methods we have, or in the case of N-shape, you actually need a potentially quite expensive sensor sitting on top of your bathtub, right? And a lot of these methods are highly sensitive to refractive index, and in no way I'll claim the method we're developing now, it's not, but it's a concern we always must have. And that's the way I would like to introduce you to digital holography. In this case, through microscopy. So it is a quite extensive field. Rade has also used it for very different purposes. And one of the most important applications of this method is microscopy. So in this case here, you can monitor, for example, the live evolution of cells in a sample. Now, what's this method we're developing called multiplexed digital holography? It's based on everything we learned from what we do in Nottingham through fluid profilometry. So you hear me talking about fluid profilometry. That's the umbrella term for anything that measures the surface of a fluid. So for example, the Fourier transform, the fast checkerboard demodulation that Leonardo mentioned, or Silke's N-shape sensor. But now we merge this with digital holography and a very simple microsome setup. So I'm sure most of you have seen one of these, but instead of having just two mirrors and one of them maybe with a piezo moving around, we just put a sample of fluid there in that basin. And you have a clear relation here between the phase of your interfered beam. So you send a beam through a beam expander. So this will have around 1 millimeter in diameter, come out to whatever size you want. And you send that through a beam splitter, you create a reference. The reference reflects back and goes through the camera. But then this bottom part here, which we call the sample beam, will probe the fluid, reflect from the mirror, and come back and recombine in the camera. This will form interference, as you probably know. And the phase of that interference pattern relates to the path length and the refractive index of the medium you're going through. Now, when you put a sample under this microsome interferometer or in the arm of a microsome interferometer, you can create this cavity effect or this multiple path, where at the reference you have this simple reflection, which is what you would normally use in microsome interferometry. But once you put a fluid, you get this new family of rays. So for example, you have a ray that reflects from the surface of your liquid. You also have rays that go through the liquid and then reflect from the bottom and leave, or do multiple reflections, eventually reaching the camera, right? These are the B rays that I call. Once you do that, you can work out some pretty nasty maths, but very straightforward, to be fair, where you can show that the interference created by the reference in all of these multiple reflections, they decouple into these different phases. And the image you would obtain is something like this. And if you zoom in, it actually looks pretty similar to what Leonardo showed you earlier, so a pattern. So instead of now putting a pattern underneath my sample, I'm generating it through interferometry. You can model that using image processing, so looks pretty much like a sum of plane waves going in various directions. The direction of that wave is determined by this vector here. And this vector we related by doing the modeling to the tilt of the mirrors, right? So if you have your reference beam and your sample mirror, as you tilt them, you modify this wave number here. So you modify the frequency of these stripes. And once you do the Fourier transform, as Leonardo did, so he explained essentially the entire reconstruction, the digital part. So I will skip there. You get that this interference decouples into peaks. That's a very nice part about this, right? In the FCD method, where you have the checkerboard, you only have two signals, one in this direction and one in this. With our multiplexed digital holography, you can generate several simultaneous signals of the same sample, right? Coming from these multiple reflections. And this is, for example, one of the simulations we did using ray tracing. So you essentially just propagate several light rays and try to form a beam and pretend you have a virtual camera there. And you should obtain something like this. And you see that the different families that I mentioned before, so reference and surface of the water, reference and bottom mirror, they really decouple in Fourier space, right? And this is the decoupling we use to then reconstruct those phases that are somewhat related to whatever is in the path, right? But then, if I put the sample there, as the light goes through the sample, it acquires the information of the depth of it, right? And that's what we use then to reconstruct really the change in depth. So what you see here is for each of those families, you have different phases over an entire region of the sample, about 15 millimeters. And I slice them and turn them into height information, which is this. And that's done through this phase to height correspondence that is written down here. Now, what's so important about this is that each of the family of rays, so RF, FB1, RBJs, they have different prefactors, right? This means that if I have a tiny fluctuation, say fractions of the wavelength, the phases acquired by each family will vary according to the refractive index that the beam went through, right? And what's so nice about this is we learned that they carry different biases as well. So you can think that the ray that went through the reference came back and then went through the fluid and came back. It integrated over all the air fluctuations of the reference and all the air fluctuations of the sample arm. However, if you think of the interference of the bottom mirror and the surface reflection, it actually is completely ignorant of whatever's happening in the reference. And that gives us a very nice way of treating the data and getting really simultaneous reconstructions of the same sample with only one image. And that's really the main message of digital holography. How much can you extract without adding much to your system from one single image, right? So from one single image, I can extract at least 4 simultaneous reconstructions of my fluid. And so I'll walk you through some of the results of a paper that we recently put out, fairly technical, definitely focused to the optics community, but really the idea is I'll finish with an overview of where we're going with this, right? So first test we did is, well, just put water underneath and see what you can measure, right? So this is the outcome. So we did get interference, nothing surprise here. So you have the stripy pattern that I mentioned we should have. When you do the Fourier analysis of this, in fact, we identified that you have those theoretically predicted peaks that I labeled again. Oh, this died. That I labeled again here. This is also dying. Fantastic. So from each of those families, I reconstructed the height. So we managed to then get height changes in the order of nanometers, as you can see here. And here's where the bias I mentioned becomes very important. So you can see that each family reconstructs pretty well the same qualitative interface, right? So you can see a trend, you can see ripples going around your sample, but some are much noisier than the other, right? And that's something you cannot achieve, for example, with the methods that we currently have. You only have one information, which is the pattern sitting at the bottom or the N shape projecting on the interface. Whereas here, we have these 4 simultaneous measurements of the same interface, right? And here we can see our gain in resolution. So as I mentioned before, we were in the order of microns, and with these results, we showed that we can go down to nanometers. And that starts maybe giving us hopes of identifying those singly quantized vortices that the helium people are very excited about. This slide really finishes with the time evolution. So this delta t here is the difference between time frames in your camera. So again, only limited by the equipment you're using, so the camera. So you can use a very fast camera or a very slow. It doesn't really matter for the method. This is pretty much what you would get out of one of the reconstructions. So I chose RB1, which is a reference in the bottom mirror. And this is a video of the surface of water when it's being driven by a small piezo from the side. So there's a decent break of symmetry. It's a square container, so you can see a very faint standing wave pattern in one direction. Very hard to see, but it's there. I'll tell you, just trust me. But really you can say, well, is this enough? We went a bit further to really test how precise and if it's really measuring anything. One of the first tests we did is to introduce a known changing volume to our sample, right? So we have a square basin, we put a syringe in, we connected the syringe to a Lego driver, very sophisticated, and we slowly filled in the sample and slowly removed water from it. The black curve you see here is the one that we obtained from tracking the syringe volume. And up here, we used several phases that you obtain from the Fourier spectrum. So I showed you before only 4 of them, but in fact, when you do the analysis, you see that several of them appears for various reasons, Fourier harmonics, digital processing errors, or really just those high-order reflections that I mentioned. And you can use all that information to then recover the phases as they change over time. You can see some of them are very noisy, this green curve here. Some are pretty much lie on top of each other. And by statistically treating them, meaning if our assumption that they all measure the same interface is correct, there should be just one set of coefficients, so set of numbers that multiplies each of these curves that will collapse them to 1, right? So I have the green curve, you have this bunch here and this bunch here. If they're measuring the same interface, and it pretty much looks like, right, the same trend, you should be able to collapse them. That's a method known as principal component analysis, very well known. But we were the first ones to implement them and merge with digital holography. And what you get is this averaged blue curve here. I must say this average blue curve includes the 1 standard deviation uncertainty. Meaning if you do this for all these 20 curves, I think, 18 at least, you can actually collapse them to 1, take the standard deviation, and that's pretty much what you get. This, of course, does not account for other systematical errors, but is really displayed that you are measuring what you're putting in. And our final measurement, I hope, and I'll finish soon, is the liquid evaporation, right? So we just monitor the interface of water and isopropanol over 15 minutes. You can do it for longer as well. And again, using the same analysis, so you have several peaks, you go there, select them, extract various phases, do this statistical method we developed. You get pretty much a good trend in all of them. Again, some of them are noisier than others. Depends. We learned with these experiments that it depends also on the sample. So we have to see how it goes on the helium. And we managed to find very decent evaporation rates. We don't have theory for evaporation rates. It was not our purpose here. Again, this is an optics paper, but pretty much in agreement with what we could find in the literature, okay, within reasonable range. Now, to conclude, I hope I convinced you can actually measure things using this method. But why is it so good as a recap, right? Well, we're now down to the order of nanometers resolutions. So we did gain almost 3 orders of magnitude in our setup. It's a very simple setup. It's a microstructure interferometer. You can go to any undergrad lab in most universities and you'll find one. But our purpose here was to keep it simple in the optics and spend a lot of time in the processing, right? And that's why we applied for a patent for this processing pipeline that we created. And we're currently trying to find industrial applications within the network grant of QCMFP and QTFP. Silke mentioned that already. But I think from the scientific side, with all of you are mostly interested in, we want to now see if it works in superfluid helium. That's the simple answer here, right? We want to see if we can reproduce what we already know, for example, from the experiments that Leonardo and Pietro discussed. Maybe we'll resolve those singly quantized vortices that Carlo is very excited about. I think there's a lot of new physics coming. Hopefully the back reaction that Adam presented earlier today will be able to identify also by doing this constant monitoring of our interface in an analog experiment for the Unger effect. And I'm pretty sure there's much to be learned from fluid interfaces. And I hope I convince you it's worth investigating a bit more and developing also new methods experimentally. Okay? So that's it. Thank you.